Here, here's my talk on what is the best soil physical property to predict soil sodicity. Sodicity occurs when the soil has a high amount of exchangeable sodium percentage greater than 15% and a low electrical conductivity less than 4 decisiemens per meter. And in the past, it has been related to soil physical properties. So many of the studies in the beginning of studying this issue measured saturated hydraulic conductivity, and to do this they applied solutions of various electrical conductivity and sodium absorption ratio to the soil, and found that as you decrease the electrical conductivity and increase the sodium absorption ratio of the solution you find a decrease in saturated hydraulic conductivity. And they have argued that dispersion versus swelling of the soil has caused the change in hydraulic conductivity, and others have related it to clay types and texture, and they have created threshold EC versus ESP curves where above a certain electrical conductivity and below a certain exchangeable sodium percentage value, the soil will have good soil physical properties, where if it's above a certain ESP value and below a certain EC level, it will have poor soil physical quality. And they have found that most of these issues have been related to the amount of smectite clay in the soil, and that as you have more smectite in the soil and more clay in the soil appears more sensitive to this solution that you are applying to the soil. And this has been found with both swelling and dispersion, and smectite is the only clay in the soil that can swell due to exchangeable sodium being within the inner layers, which can cause the inner layers to expand apart and cause swelling of the soil matrix. So the objectives of this study is to determine soil properties that can determine smectitic soils from non-smectitic soils, and we would like to compare soil properties related to soil swelling related to changes in soil hydrologic properties on these soils and see whether there's a relation. So for this study, we selected 3 soils from South Dakota that were all silty clay loam texture, which were predominantly smectite and illite clay, and a silty clay from North Dakota, which is the Fargo soil, which was predominantly smectite and illite clay mineralogy, and Port Wing soil, which is a clay loam that's primarily illite clay mineralogy, and Cecil is a predominantly kaolinitic soil and was clay textured, and we created synthetic soils mixing pure clay minerals, which was a Wyoming bentonite, a Georgia kaolinite, and a Fuller's earth, and we mixed that with silt to create mixes between 20% clay and 70% clay, which was the pure clay minerals. X-ray diffraction on the clay minerals found that the Wyoming bentonite consisted of primarily smectite, that the kaolinite consisted primarily of kaolinite, and the Fuller's earth was a mixture of polygorskite and smectite. For the methods, we measured the Atterberg limits, the coal rod method, water retention, and saturated hydraulic conductivity. Before measuring the water retention and Atterberg limits in coal soils were treated to salt levels ranging between 5 milliequivalents per liter and 40 milliequivalents per liter, and all the 10 milliequivalent per liter treatments except the ESP50 treatment were made using calcium and sodium chloride mixes. All the 20 and 40 milliequivalent per liter treatments were made using sodium and calcium chloride salt treatments, but for the 10 milliequivalent per liter ESP50 treatment and the 5 milliequivalent per liter 6 through ESP50 treatments, the treatment was made using sodium carbonate treatment of a soil that was treated to 5 milliequivalents per liter with calcium chloride. And then the soil was crushed and passed through a 2 millimeter sieve. So treating the 3 soils that were of similar texture and the same mineralogy to the same ESP and EC levels made the calcium saturated soil behave very similarly. The 5 milliequivalent per liter treatments, except the 5 milliequivalent per liter ESP0 treatment, are made using a dry treatment applied to a calcium saturated soil, where the 40 milliequivalent per liter treatments are made by using sodium and calcium chloride solutions. And we found that soil liquid limit increased gradually as ESP increased at 5 milliequivalent per liter, and it really increased between an ESP of 15 and 50, and that at the 40 milliequivalent per liter there was no increase in soil liquid limit. And the same was found for plastic limit, and the soil plastic limit did not change. This agrees with what has been found with the other measurements, that at low EC and high exchangeable sodium percentage, the soil has the greatest increase in swelling of the soil as measured by the liquid limit. Soil coal had similar effects as the soil liquid limit, but it wasn't to as large of a degree, and there was more of a variation in the individual treatment measurements with soil coal than there was with soil liquid limit. But soil coal did have the same responses, with the 5 milliequivalent per liter treatments gradually increasing as ESP increased in the soil, and the 40 milliequivalent per liter treatments having very little change as ESP of the soil solution increased. So with these measurements, we found a statistical difference, but it wasn't as large as we would expect if the soil was behaving like a Wyoming bentonite in the smectite fraction of the soil. So we decided to measure the liquid limit on 3 other soils besides the initial 3 soils that were used. One which was a smectitic soil that had more clay and smectite in it, and a mixed clay type soil and a kaolinitic soil. And in this study, we found that the smectitic soils increased in liquid limit as the ESP increased, and the non-smectitic soils had no change or a slight decrease in liquid limit as the exchangeable sodium percentage increased. Further showed that you can use soil swelling related properties to identify soils that contain smectite from soils that do not contain smectite. So we were able to distinguish the difference between smectitic and non-smectitic soils using these swelling measurements. Then when we measured the soil liquid limit and plastic limit on clay silt mixes with the sodium saturated clays, which is the Wyoming bentonite or sodium smectate, and we mixed half sodium kaolinite and half bentonite and sodium kaolinite, and we measured the liquid limit on them and plastic limit on them versus clay content and treated to clay percentages between 15 and 70%, and we found that as percent clay increased, there was linear increases in plasticity index and liquid limit, and that there was almost a linear increase in liquid limit with percent bentonite in the soil, because bentonite has much greater plasticity and liquid limit compared to the kaolinites. And when we applied the sodium saturated soils compared to the sodium saturated clay mixes, the sodium saturated soils had much lower plasticity index, or which can be converted into clay activity, compared to the kaolinite bentonite mixes, and barely plotted above the sodium kaolinite on the curve, although the soils were primarily illite and smectite, so they should at least behave closer to the half smectite, half kaolinite line. So for the calcium saturated state, or the 0% ESP state, I took Fuller's Earth, which is actually a mix of polygorskite and smectite, but its liquid limit and plasticity index were very similar to published values for calcium smectites. And I mixed that with the silt mix, and I mixed the kaolinite with the silt mix, and I mixed the 50-50 mix of calcium kaolinite and Fuller's Earth, and I found that As you increase the amount of Fuller's earth in the sample, the plasticity index linearly increased, and that the soils all plotted between the half kaolinite, half Fuller's earth mixed and the kaolinite mix. So their plasticity was much lower compared to pure smectite minerals also, and that the soil smectites are still not behaving the same as the pure smectite minerals. So identifying the clay minerals by X-ray diffraction and assuming water uptake by clay minerals you identify in a soil as smectite is not going to be the same amount of water that will uptake as a pure smectite. So McNeil's hypothesis that the soil smectites behave like a Wyoming bentonite is incorrect. When I measured water retention curves on the Aberdeen, X-Slide, and Harmony soils, I measured them on the same cell treatments as were used for the initial study on soil Atterberg limits, with some dry treatments and some sodium and calcium chloride treatments, and I found as the ESP increased at low salt concentration, water retention increased at potentials greater than minus 10,000 centimeters and became farther apart as you approached saturated water content. And if you increased the salinity level, the water differences in water retention were much smaller, which is the same response that was seen with soil coal and soil Atterberg limits, that high electrical conductivity can reduce the change in the property that is expressed by high exchangeable sodium percentage because you're reducing the swelling behavior by having a high osmotic potential in the solution, preventing water from going into the inner layers of the clays. So then I decided that measuring water content at some wet water potential, like a third bar or minus 1/3 bar or greater, could be an indicator of soil sodicity sensitivity. So I measured this on the Aberdeen, X-Line, Harmony, and Fargo and Port Wing soils, and I found that there was a small increase in the mixed clay type Port Wing soil and the Cecil soil in water retention as ESP increased, and there was a large increase in the smectitic soils. And when we got to the ESP 100 treatment, though, we started to build up salinity to where the water retention didn't increase anymore because we're starting to build up salinity. And then I fit the water retention curves with the Van Genuchten equation, and the only major difference in the Van Genuchten fitting parameters was the saturated hydraulic conductivity I measured and the saturated water content, which makes sense because we're just increasing clay swelling due to the high exchangeable sodium percentage at low salinity levels, which seems to appear what's happening on the smectitic soils, that you're increasing swelling of the clays, which is increasing water retention. So for the hydraulic conductivity data, there was much larger variation in the hydraulic conductivity data, as you can see with the squirrely lines in this data where it's ESP, and at the 40 mil equivalent per liters, there was no difference between the ESP level we created of 0 and the ESP level we created of 25%, whereas at the 5 mil equivalent per liter treatments, there was a very large difference in hydraulic conductivity in the smectite dominant soils, and in the non-smectitic soils there was still a large decrease in hydraulic conductivity, but it was only like a 10-fold magnitude instead of a 100-fold magnitude. So our conclusions is soil liquid limit and water retention at 1/10 or 1/3 bars are the best indicators of sodium sensitive soils, and the soils with the largest increases in liquid limit at high SB and low EC also had the largest changes in soil water retention and hydraulic conductivity. So the swelling properties increase does agree with large hydraulic conductivity changes in the soil, and that increases in whole soil liquid limit and water retention at wet water contents is clearly linked to the response of smectite clay being within the soils.